Hi everyone. Okay, so 10.2. 10.2 is going to be a repeat. It's going to sound so familiar of 10.1. The only thing that changes is really the formulas. And again, everything is in your reference paper. So let's go ahead and get started. Sampling distribution. So this one, slightly different. Your shape, if N1 or N2 or N1 and N2 are normal, you can assume that their difference is normal. If they are both greater than or equal to 30, you can assume normality. If you graph them, if they're less than 30 and you graph them and either one has extreme skewness or outliers, then again, you can assume normality for their difference. The center, your mean or your point estimate, whichever, is going to just be the first average minus the second average. And then your spread or your standard deviation, worst part about the whole thing is going to be plugging it on the calculator. It's the square root of the variance. Your variance is your standard deviation squared over N1 plus your second standard deviation squared over N2, as long as you meet that 10% condition. Your two sample test statistic, again, I already went through that, so you're going to go through random, 10%, normal, large counts. You can read through that if you want to, but it's just all a review. Confidence intervals. There's your formula. Again, it's on your reference paper. You're going to subtract your differences. Please make sure that you clearly label what your mu1 is and what your mu2 is, because order does matter, obviously. To find that t value right there, that t statistic, again, this is a little bit different than a z statistic, because with z, it stays consistent. Like a 95% confidence is always 1.96. With t, it is not. So remember how we do that is you sketch your normal curve and you put whatever percentage. Let's just use 90% as an example. So if I want to be 90% confident, then I put 90 on the inside. So that would leave 10% left over for the outside, because remember, under every density curve, it's 100%. So 10% left, which means that this side is 0.05 or 5%, and that means that side is 0.05 or 5%. So to figure out what this t value is right there, you would go to the calculator and you would do inverse t, and then you would do the area of 0.05 and then comma your degrees of freedom. And it says here your degrees of freedom is the smaller of N1 minus 1 or N2 minus 1, whichever one is less. So if you have one is sample size of 10 and one is sample size of 20, then you would go with the 10 one because it's smaller, and 10 minus 1 is 9. So 9 would be your degrees of freedom. And in case you've forgotten where to find that stuff, I'll go over it again later. But on these calculators, it's second distribution, second vars. And then there's your inverse t right there. If you're on the Inspire, then everything is under menu, either probability or statistics, and then distributions, and you'll find it in there too. Okay, so let's go ahead and go through an example of a confidence interval. So we've got Ashton and Olivia, and they want to know if generic chocolate chip cookies, excuse me, have as many chocolate chips as a name brand cookie. So basically what they do is they randomly select 10 bags of Chips Ahoy and 10 bags of Great Value. They randomly select one cookie from each bag. They carefully break apart each cookie and counter the number of chocolate chips in each. And there's the results. So 10 cookies and how many chips are in each one of those cookies. So this time we're going to use a 99% confidence to estimate the difference in the mean number of chocolate chips between those two cookies. So as with any confidence interval, we're going to start with our state. We wish to estimate mu1 minus mu2. Make sure you label what mu1 and mu2 are. So mu1 is the average number of chocolate chips in Chips Ahoy cookies, and mu2 is the average number of chocolate chips in Great Value cookies. Oh, sorry, there's a little typo. That should not be 95. That should be 99% confidence. And I'm pretty sure I did do it right down there. I just wrote it wrong right there. Okay, plan. Remember, in plan, you need to name your test. All comes from the reference paper. So we will use a two-sample t interval for mu1 minus mu2. Random, they randomly selected 10 bags and then randomly selected one cookie from each one of those packages. 10%, assume that there are more than 100 bags of cookies because they chose 10 bags, and we do 10 times 10 for that 10% condition there. And then normal large counts, we do have an issue with that because there are only 10 cookies of each kind. And remember, they either need to tell us that it's normal, which they did not, or we need at least 30 of each, which we do not. There's only 10. So that's why if you look up here, I did graph this. This is what a parallel box plot would look like on a TI Inspire. So I'm looking at that, and I'm looking for two things. I'm looking for extreme skewness. There might be a slight skew to, especially the Chips Ahoy one looks like there might be a slight skew, but nothing, excuse me, nothing extreme, and there's no outliers. So we are okay to assume normality. Now the next part here, let me see if I can zoom in a little bit. So then what I did was I entered in to a calculator, or to, you could do this in Excel or Google Sheets, whichever. I entered in the data and I found the mean and the sample standard deviation for either. Yes, it's a sample standard deviation because it was a sample of cookies. So found both of those data points. I also needed to find out what my t-value was. So again, to do that right there, what I would do is I always sketch this, and I'm going to put 99% on the inside there. So that leaves 1% for the outsides. 1% would be 0.05%. Oh, I'm sorry, 1%. Half of 1% is 0.5%. And then 0.5% as a decimal would be 0.005. Okay, and that's where I came up with that area right there. Okay, so 99% on the inside, that's my confidence level. That leaves 1% for the outsides. There's two sections, so you take that 1% and you divide it in half, which gives you 0.5%. And then you convert that or divide it by 100, which will give you 0.005. There are 10 bags. 10 minus 1 is 9, which is my degrees of freedom. So this is my area. This is my degrees of freedom, which gave me that as my t statistic. Over here is the formula. You take the first mean minus the second mean. Order does matter. So I said mu1 was the number of chocolate chips in Chips Ahoy. So I would take my mean for Chips Ahoy minus my mean number of chocolate chips for Great Value. And then I'm going to add and subtract it at the t-value times, again, this is the worst part, is you do the standard deviation squared, or the variance over n1, plus the standard deviation squared, or the variance of the second sample, over n2. Plug that all into a calculator, and you get this interval right here, negative 4.81 to 2.81. Now, there is something about that interval that you should notice. 0 is included in that interval. So conclusion, we are 99% confident that the interval from negative 4.81 to 2.81 contains a true difference in the average number of chocolate chips between Chips Ahoy and Great Value cookies. Since 0 is included, we do not have convincing evidence of a difference. So if 0 is ever included, then you do not have convincing evidence of a difference. Basically saying you subtract one from the other, you get 0. There's no difference between the brands of chocolate chip cookies. Okay, so then the next thing that we need to talk about, again, we just did a confidence interval with two means, and now we're going to do a hypothesis test. So what changes here, again, is the formula. We're going to be using a t-statistic, again, because this is means, and with means we always use t. This right here, the hypothesized difference is always 0, so that part is easy. So you're just going to subtract the two means right here, and then divide it by the standard deviation of the standard error, and the standard error is the standard deviation of the first one squared over n1 plus the standard deviation of the second one squared over n2. All on the reference paper, no big deal there. Down here, for your degrees of freedom, your minimum of the smaller of the n1 or n2, whichever one's smaller, and then minus 1. And again, that's all on the reference paper, so nothing that you need to memorize. After buying many helium balloons, only seemed to deflate within a couple of days, Aaron and Jenna decided to test whether helium balloons deflate more quickly and air-filled balloons. To find out, they bought 60 balloons and randomly divided them into 2 piles of 30, filling the balloons in the first pile with helium and in the second pile with air. Then they measured the circumference of each balloon immediately after it was filled, and then again 3 days later. The average decrease in circumference for the helium balloons was 26.5 centimeters with a standard deviation of 1.92, and the average decrease of the air-filled balloons was 2.1 centimeters with a standard deviation of 2.79. Now, without even doing this, you should be able to tell that we should definitely get in the end that we have convincing evidence that one would deflate more quickly than the other. But anyways, state. Make sure in state that you label which is which. So I have mu1 is helium, mu2 is the circumference, that should say air, of the air-filled balloons. Alpha is 0.05, and then here is my my hypothesis right here. So the first one's always that mu1 equals mu2, and my alternative is that the circumference of the helium balloons, the decrease will be greater than the average decrease for the air-filled balloons. Part plan, first thing you need to do is name your test. So we have a 2-sample test for the difference in the means. Randomly divided the balloons into 2 different groups. 10% condition, assume that there's at least 600 balloons, and I got that by taking my sample size of 60 and multiplying that by 10. And then normal large counts, both the samples are equal to 30, so you can assume normality. We do not need to graph in this situation. Worst part is plugging it in on the calculator. So let me see again if I can zoom in. I don't know if that makes that any clearer for you. But you take the first part, you subtract the 2 means. So the one was 26.5 minus 2.1. That came from right up here. Minus 0, that will always be a 0 there. And then you're going to divide that by the square root of the standard deviation for the first one squared over n1 plus the standard deviation for the second one squared over n2. And again, the standard deviation squared is also called the variance, in case you cared. Plug that in on the calculator, and you may want to practice plugging that in. Worst part about the whole question is really just making sure you can plug it on the calculator. Now again, look at how many standard deviations away you are, because t is another way to measure the exact number of standard deviations away you are. You are 39 standard deviations away. 39 standard deviations away. Like, you really do not need to plug this in on the calculator, because if you are 39 standard deviations away, so my minimum, my maximum, and my degrees of freedom, I don't think excuse me, the calculator would even give you an answer. Notice I did a TCDF because it's a t-test, and you should also include somewhere a sketch of this. Again, I'm 39.4602 standard deviations away, and then I'm going to shade to the positive direction there. Approximately 0. So then the conclusion, since P is less than alpha, P is small, we reject the null. We have convincing evidence that the average decrease in circumference of the helium balloons is more than the average decrease in circumference of the air-filled balloons. Now, I did say to interpret the p-value. Now, the p-value is this value that you got right here, this 0. Okay? So when you're interpreting the p-value, a lot of people think that that's just concluding, and it's not. It's different. Your p-value is assuming that the null is true, assuming that there's no difference. Then what is the probability of getting the sample data that we did? And that for us is approximately 0. If there was no difference between the the decrease in the circumference of a helium balloon and the decrease in the circumference of an air-filled balloon, if there was no difference, then it would be almost impossible, approximately 0, almost impossible for us to get the sample data that we did. Okay, so therefore, the null is probably not true. If this was true, for us to get what we did, it would be almost impossible. So therefore, that is probably not true. Okay, so please make sure you can interpret a p-value. If you need help with that, let me know. And last but not least, this example right here, We want to know if students perform better on tests when there's no distractions, such as a teacher talking on the phone. We have 2 classrooms, 30 volunteers. So the first experiment I'm going to talk about is a 2-sample t-test. So what we would do is we would randomly assign students, the 30 volunteers, to one of the 2 rooms. So what I did was I put the letter A on 15 index cards and the letter B on 15 index cards. I shuffled them and handed them out to the volunteers. Anyone with an A goes into one room, a B goes in the other room. A will take a reading comprehension test while someone's talking on the phone. B will take the same reading comprehension test with no distractions, and you calculate the average test score to compare the 2 groups. Now, here's the problem with that. There could be different ability levels. So just by chance, what if randomly students who were a little bit higher achieving ended up in one classroom, and students who are a little bit more low achieving ended up in the other classroom? You're comparing, there's another variable that's lurking here, a confounding variable. So to decrease that variability, what we could do is what we call a matched pairs experiment. And we have talked about this a couple times, but matched pairs is when you do the same thing to the same person. So what we would do, still randomly assign students to different rooms. So write A on 15 index cards and write B on 15 index cards. Anyone with an A goes in one room, anyone with a B goes in another room. Excuse me. They still take the same reading comprehension test. Okay, that does not change. One room, let's say A, has someone talking on a phone, B does not. After 30 minutes, give them a short break. They go back into the same room that they've been in. They're going to take a similar reading comprehension test, but this time, group A will not have any distractions and group B will have the distraction. And then what you're going to do is you're going to compare the results to each student. So if I was in group A, I would take the first test that I took and the second test that I took, and I would compare those results to my test. So therefore, I'm eliminating any variability that's due to achievement level, like pre-existing achievement levels, to really focus in on, is the distraction the cause for the increase or the decrease in the exam scores. Okay, so read over that when you get a moment. It's a good example of a matched pairs experiment, and it comes up often, so you're going to want to know what that is. And for that one, you would do a 1-sample test, because you would be looking at the differences between the 2. The first one, you would do a 2-sample test because you're comparing 2 different populations. Anyways, okay, so that finishes up 10.2, which actually finishes up chapter 10. So we are done with this type of hypothesis testing. Chapter 11 is going to get into 2-way tables and how we would make hypothesis about 2-way table data. So use your reference papers, look through anything, and let me know if you have any questions.